All right, so your assignment number 2 has been released. You can take a look at the instruction there, but please just notice that here, especially for the programming part. So I decided that we are still going to stick to the edge list implementation strategy. Okay, so you stick to it, the things that you kind of study for assignment number for test number 1. I'm going to release the guide by next Monday. So maybe over the weekend, I'm going to give you the guide to give you a little bit more detail about the programming part for your test number 2. But you can expect, very likely, I'm going to give you some working version of maybe BFS. You will be given of breadth search. Given. And of course, that one is going to be the solution version, which I'm going to give to you next week, right, after the submission deadline. So that one there, you're going to make sure you study carefully. That one there closely correspond to what we actually cover about the tracing for BFS in the lecture. So that's something will be given to you during the test. And what you will be asked to do will be maybe to answer some graph question. It's possible. Okay, so that will be the task you may be asked to do, okay, during the test number 2. For example, for your assignment, you were asked to, based on the BFS, for example, you can actually calculate how many connected components there are using the BFS, right? You just gotta somehow add a loop and maybe keep some local variable, add some additional attributes, etc. Right? So you may just want to go over the list of questions that we talk about, how you can adapt BFS into. Right? So that's something you want to think about. I'll write it down more precisely in the actual guide by next Monday. But we can talk a little bit more once I release the guide on Monday's class. Apart from that, definitely you want to pay attention to the written question as well, especially about how to trace breadth search. That's something very similar to test number 1. And also the Dijkstra algorithm. I'm pretty sure there will be some question about it. Right? So I think for Dijkstra, there'll be 2 parts you want to definitely pay attention to. Number 1, you want to know how it works in terms of the tracing. I think for the tracing part we already finished covering that from Monday's class by that example. So I think also complete the paper exercise about the Dijkstra algorithm on the more complicated example and make sure you're fluent with it. And the second part, which I'm going to talk about today, is more about idea about looping variance and also certain properties I want to revisit about the Dijkstra algorithm, especially why we actually got a non-negative weights assumption. So we're going to look at one counter example today, just to give you the idea. Okay, and of course there's a proof question there on one of the questions on the paper exercise. And the proof about Dijkstra algorithm is very standard. You can easily find it on the Google, on ChatGPT. I don't mind, seriously, because I just want you to learn the stuff. If you can somehow study, if you really have no clue, I don't mind, you can either ask me or you can simply search for some standard solution, but try to really put the proof in your own words so you will know inside out exactly how the proof is supposed to work. I might ask you some insights about the proof in the test or definitely on the exam. Okay, so don't worry about anything about plagiarism. There's no such thing for our assignment in our context. I just want you to learn the stuff at some point. Okay, and then the actual test will be on November 24th, right? Not next Monday, right? It's being postponed for 1 week. Question? All right. Anyway, I'll give you more information later. All right. Let's now do a very quick recap from Monday. Okay, we did this complete tracing here. I don't need to repeat, but there's something I might have to come back and refer to it, especially when we talk about after removing every vertex at the end of each iteration. You can see I put down explicitly this final condition here. This is something we're going to go and actually check today. All right. This actually, I can tell you now, this is the actual looping variance for the Dijkstra algorithm. And this is also going to be the key for you to actually prove about the correctness of the algorithm. That's something I'll get into a little bit later today. All right, I'll get to it. Okay. So there's a reason really I kind of emphasize about the result being final versus not yet final. The result is final as soon as the vertex is removed from the priority queue. That's very important. Okay. All right, just make sure you follow the format, same format as well for your assignment number 2. It's going to be a little bit tedious, I know, when you get more and more iterations, but if you want to type it out in Word, or if you want to just write out on the by pen and paper, that's okay, as long as you know the exact steps for each iteration. I think that's the most important. And also notice about the order in which we can extract the minimum capital D value from the priority queue. That's also something important. Okay. All right, and then this is just about computing the ancestor path and also the shortest path. Something that's really nice about the Dijkstra algorithm is you don't really have to keep like a list, like an array list of nodes along the way. You don't have to. All you got to do is just keep the ancestor for each node and update them as you need it. Right? So once you calculate at the end, once the algorithm terminates, you can calculate the ancestor path accordingly. And then do the reverse, you will get the shortest path, right? That's something we kind of did from scratch from Monday. So also make sure you understand about the difference between shortest path versus ancestor path. They're different, but they're related. Okay. And then we kind of started talking about correctness of loops. Okay. So the loop syntax we're assuming is about just using the while loop. Okay. But of course, you can easily convert while into the for loop, right? That one we wouldn't go. Okay, you can assume, for now, we just talk about while loop. And the Boolean condition here, we assume as long as this is true, we're going to keep executing the body for another iteration, right? That's kind of basic, right? So think about the B here is what I call the stay condition. As soon as B becomes false, that means we are ready to exit from the loop, right? Just make sure the loop can terminate. For Dijkstra algorithm, the number of iterations for the outer loop will be the number of vertices initially in the priority queue, which will be all the vertices. So we wouldn't touch upon the running time for Dijkstra just yet. I'll do that first thing on Monday. So Dijkstra algorithm running time will take a little bit more insights, but let's wait until Monday. But I'll do other things today first. Okay. All right, let's now develop from here. Okay. Let's think about how, and of course, this page here is just about precondition and postcondition for Dijkstra algorithm, right? What's missing here is about how do we actually eventually reach to the postcondition. To really go there, you don't really just go directly from precondition to postcondition, right? You don't really directly go from here to here. Somehow you will have to see what will be the progression we are trying to make between iterations. So there'll be something we're going to see. It's called loop invariance. Let me introduce the concept, which is pretty straightforward and simple, and then we do some simple example today. And then I'll show you another example together on Friday in person, right? No Zoom. It's got to be in person this Friday. Okay, we're going to talk about some loop invariant exercise as well. Okay. Okay, let me develop from here. Just want to make a few more annotations. Let's understand about loop invariance, first of all. If you look at the slides, okay, so that's the syntax we assume. Every time you have some while loop, and then you have certain assumption, precondition on the input, and there will be certain expectation on the output, which we call postcondition. Okay, and then we're going to talk about something called loop invariance. So just for your knowledge, in this course, we only talk about just correctness, but it's so-called partial correctness, in the sense that we don't really try to prove that the Dijkstra algorithm, for example, is going to terminate. We just observe that, see the pattern. However, to be completely formal, you will have to specify another thing, which is called loop variance, to really measure about termination. But it's not something we're going to do in this course, right? So the part about loop variance is only for your knowledge, but we're going to focus on loop invariance, okay? For arguing about termination, we can just observe the pattern for the loop counter and see how exactly it's going to terminate. But focus on loop invariance. And what is really loop invariance, okay? So loop invariance is basically a Boolean condition, right? So of course, for the Boolean condition, you can either specify using the conjunction, disjunction, universal quantifier, which we'll try to see maybe on Friday's exercise for loop invariance. Anything you can specify as a predicate or Boolean condition can be treated as a loop invariant. It's simply like a middle point you want to evaluate to be either true or false at the end of each iteration, for example. Okay, we'll get there. So these are the two important aspects you want to remember about loop invariance. We'll see an example very soon. You want to make sure loop invariance is going to be established right before the very first iteration. You want to make sure the loop invariance maintained between each iteration. In some way, loop invariance is more like an inductive proof, right? So think about, we have some inductive hypothesis right there. It's like a loop invariance. And then you want to make sure the base cases will actually satisfy, at least for the small input. And then you want to show that from input size k to input size k plus 1, almost like from iteration k to iteration k plus 1, the next iteration, the loop invariance also maintained, right? A little bit like an inductive proof, similar. All right, so let's now take a look at the syntax, right? I also try to show to you how you can run this potentially in Java. I'll try to prepare that either on Friday, or maybe I can show you that in class, maybe next week, okay? But the idea would be you can use some assertion. I'm not too sure if you did that before, maybe in Java. There's a way for you to run assertion. Assertion is like a JUnit test assertion. Basically, you want to assert certain Boolean condition at this point. If the assertion is true, go ahead with the execution. If the assertion is false, you kind of stop right away. There's some violation there, okay? So we got the precondition check and postcondition check, right? We got precondition right here, and also we got postcondition. You can think about the precondition will be checked right in the beginning, and the postcondition will be checked right at the end, right? So beginning and the end, pre and postcondition, first of all. And then we actually got some initialization, okay? So this will be whatever steps you have to take before you even try to run the loop for the very first iteration. Okay, so here you can think about init right here. The intention is you are trying to use this part over here for your algorithm to really try to establishing the loop invariance. Okay, some Boolean condition. And then the very first time you check for the loop invariance is right here. Okay, let me just write it right here. So this is the very first time. Right before you check the Boolean condition B to see if you want to run for the very first iteration, right? So you can think about check for the very first time. If that's true, you go for the first iteration. But before that, you try to make sure the loop invariance is already true, right before the loop. Okay? So this one here is the first, it's more like a base cases, okay? So this part here is to be sure, assertion is like asking, is the loop invariance established? Number one, all right? Of course, you can go on to really execute the loop for as many times as needed, and then at the end of each iteration, think about the very last step in the Dijkstra algorithm. As soon as after we remove the vertex from the queue, we check the loop invariance right away, okay, at the end. So that one there, right here, assert I. Okay, it's actually at the end of each iteration. So this one really is asking another question. Is the loop invariance maintained or preserved? You can use either way, okay? Preserved or maintained. At the end of the current iteration. Okay, so these are the two critical questions we have to see. Right? Of course, we can check it at the runtime. Okay, maintain at the end of the current iteration. Okay. Okay, so far so good? Okay. So after this, let's now take a look at one flow chart just to see how things can be checked. Okay. So let me just get my notes here ready. Okay. Okay, so what we have is right here. Okay. Let's now take a look at the flow chart here, right? It's not complicated, right? Just make sure you know where you are. Okay. So think about at this point here, we check to see whether or not the precondition is satisfied. If it is not, we got precondition violation, right? So at this point here, we check the precondition. And then if the precondition is satisfied, we go ahead and execute the initial part is not part of the body of the loop. We just want to do something before the very first iteration of the loop. So after this particular part here, we're now asking whether or not the loop invariance is established for the very first time, right after init. Loop invariance established. That's the question we're asking. Okay? If it is, then go ahead. Otherwise, there's going to be loop invariant violation. Okay? And then, given that loop invariant has already been established, let's now check to see whether we should bother with even one iteration. So you're going to check to see whether this Boolean condition here is true or false. All right? If the Boolean condition is true, right, we just go ahead and for the very first iteration. We'll talk about this a little bit later. Right? Post condition usually will be checked at the end. Okay? So if you're able to go for this route over here, right, the B is actually true. That means you're going to stay for another iteration. Either it's the first one, second one, and onwards. You're basically going to stay for another iteration. And of course, this condition here is going to check. Should we stay or exit? By just checking B right here. Right? I'm just trying to show you the one-to-one correspondence between the flowchart and also the code. Okay? And then once we get into the loop, and we run one iteration by executing the body statement of the loop. Now at the end, right here, we're going to check one more thing. Okay? At the end, we're going to check to see whether or not I'm just missing one arrow over here. We should really go back here. All right? Just go back. Right? I'll fix the diagram later. But you can think about at this point here, we're going to check to see whether the loop invariant will be maintained. Okay, right here. At this point here, we're going to see whether the loop invariance is maintained. Okay? If it is not maintained, we're going to get loop invariant violation. Okay? So you can think about there should be, yeah, I definitely got to fix the diagram. I'll do that. Okay. You can think about right here, if the loop invariance is actually not satisfied at this point. Okay. Think about this point here is actually not loop invariance. That way, you're going to get loop invariance violation. If you don't have that loop invariant violation, you can actually go back to the beginning of the loop right here. And then you can do another check on B to see whether you want to execute for another time, right, for the iteration. You basically go on and on and on. Loop invariant is only checked at the end of the loop. Okay? Right, one final thing to see. We want to see as soon as we exit from the loop, we want to see if the post condition here, overall for the algorithm, the output is going to be correct. So at this point here, you can see that the condition here is not B. So think about right here. Not B means we're going to exit from the loop. When we exit from the loop, and then we check to see whether R is actually satisfied. Okay? Once we exit, you want to check if the post condition R is satisfied. In case it is not, in that case, we're going to get post condition violation. In case it is, you can see R is actually satisfied, and then you will actually go into the final state where we just say algorithm is correct. So this will be the final path we'll like to reach right here. Okay, just right here. I'll go a little bit better. You'll simply go for this path right here. Right? So this will be the final state we would like to have. That means you exit from the loop and also the post condition is satisfied. Question? Anything that's not clear? Let me recap, and then we'll do one example together. Hopefully that will be very clear. So loop invariance is really some additional assertions that we are trying to add to our loop. Okay? You're inserting your loop invariant check in two places. One will be right before the loop. Another one will be at the end of each iteration. Okay? Make sure loop invariant is established and also maintained between iterations. All right? Of course, your challenge would be, there are two possible ways to really ask you a question. Oh, let me just say that and then I'll take your question. There are two possible ways I can ask you a question, at least two possible ways. One would be, I can give you some looping variance and also the loop. I might ask you, is the looping variant always going to be established and also maintained? If not, tell me which iteration is going to fail. Okay, you will see one exercise on the slides. Okay, we can talk about it as well. Another way I can ask you about, which we can do one exercise thoroughly on Friday, will be I give you the algorithm, and then I can ask you to specify the looping variance for me. That'll be another way, right? These are the two typical questions I can ask. Okay, Josh.
Since we test the looping variance before the loop and then after each iteration, wouldn't it make more sense to think of it like we do the loop and variance check before we start a specific iteration? Like we do the loop and variance check before we start loop 1, and then, you know, we do that loop 2.
Yeah, that would be one way to, well, we just want to, well, it's a bit like when you talk about mathematical induction, right? You can split between base cases and inductive step. So it's a bit like that. We want to say, when you actually do, before the loop, you want to check for the very first time, right before the loop, make sure it's established. And then you decide whether you want to really go for the loop for the very first time. And then after the first iteration, you check it for the second time, and then so on, right? Just the order. Yeah. It might be that you want, I know what you mean, you want to somehow put that assert I as the very first one. What if, for example, I can tell you why. Let's say we don't have these two. According to what you said, simply insert as a first line. Assert I, right here, right? In that case, what if the looping variant is not really established, but you don't even have an iteration at all? In that way, you don't really have a way to really signal an error for looping variant being established.
But like the way you have it written, I thought that the establishing of loop and variance and the doing the mid-loop loop and variance check, like it's just assert I. So
assert I.
It's the same condition.
Yeah, I see. You just want to, yeah.
It's the same condition, like when you start it in the loop versus starting it just before the loop, like that doesn't really change anything programmatically.
Because the difference goes like this. If you only put assert I here, let's say, in that case, what if the B is false right away? That means you don't even have a very first iteration. In that way, you never get a chance to signal an error about a looping variant being established. You see what I mean? Yeah, let me write it down. Okay. It's a good question. So let's say we have the while loop. Alternatively, while some condition here, and then we got S in it. And according to what you're suggesting, we can simply put assert right here only. Assert I, for example, right? Over here. But the problem is, we're saying, if B is false right after S init, then we will not even get a chance to check the looping variant here for the first time. Establishment. Yeah. It's more like an edge case that we are handling here, really. Yeah. So it's better to make sure it's established, and then afterwards we make sure every subsequent iteration, including the first one, at the end we check to see maintenance. Conceptually, it's a bit better. Yeah. You only check to see whether it's maintained after you have done something for that particular iteration. Okay. It's a good concern, but that's the way we are defined. All right, so let's now do one example about the looping variance, okay, right here, okay? Very simple one, just to get very clear about the meaning for that, okay? And then let's just see this, right? Let's now highlight the looping variant first of all, okay? Let's say we got precondition here. So this is a precondition. Make sure I value is equal to 1 to start with. And then post-condition, we want to make sure I is exactly equal to 6. Okay, precondition, post-condition. And then you can think about the algorithm, which I'm going to highlight in gray. Oh, sorry. This is the actual algorithm. While loop, some increments, and also right here. Okay, so the gray part is just the algorithm itself, while loop and some variable assignment. Very simple. Okay, and for the looping variant, we're going to duplicate the line, yes, and then we're going to do right here. So we're going to do assert looping variance for establishment. At the end of each iteration, we're going to assert the looping variant is maintained. Okay, right, that's what we have. Okay, so this one here is precondition Q. That's the postcondition R. And this particular Boolean condition, and we're only using a conjunction right here. Pretty simple, but we're going to see how you can use a universal quantification, for example, on Friday when we do that exercise together. Okay, so this one here is the looping variance. Okay, Boolean condition. I'll write it down more explicitly. So looping variant we have is 1 less than or equal to I less than or equal to 6. Okay, that's what we want to focus on. Okay. Let's now try to trace. Of course, it's kind of trivial to trace exactly how I is going to change. Oh, let me ask you guys. How many iterations will there be for this loop? How many? How many iterations? 6? How many iterations? 6? Well, anybody got different answer? Are you sure 6? Are you sure? 5, right? Careful, okay? Maybe trivial, but careful, right? Okay, 5, all right? Okay, let's now trace it out, okay? I think the actual tracing, like how I is going to be changed, is trivial. I'm pretty sure you can figure that out. I just want to show you about the pattern, about the changes, okay? Let's now do a table, okay? So we can also use that correspondence, the correspondence from the table to see Dijkstra a little bit later. Okay, I'm going to be very, let's be complete about all the ingredients. Okay, so we got the iteration number. Okay, and then we got I value. And then we got looping variance, whether or not it's true. And also we got the condition, B. This is the B, right? That's the state condition. Think about this is B, okay? Let me just remind you, the B here is about whether or not we want to stay, the state condition. Okay, and then we got post condition at the end. All right, like that. Okay, so initially, there's nothing we did. Actually, you can see before the actual loop, we didn't do any sinit. So sinit, actually here, may well be just empty. That means nothing to be done. Okay, it's possible. Okay, so here you can see the I here, we assume that I is just an attributes. So we assume I, at the point that we call this algorithm test li, is going to be 1. That's something we assume. That's why we check the precondition, right? Or if you want to explicitly assign I to be something, that's also possible. But for this case, we assume it's going to be the case. So let me explicitly write this out as init. Okay, init. Okay. In this case, the I value is assumed to be 1. Okay, and now, when we now check to see this looping variance, which means I should be between 1 and 6. That should be true. Right? That means the looping variant is established before the first iteration. And at this point, we check to see whether we should really go for the very first iteration. I think we should, right? If you check 1 less than or equal to 5, true. Okay, go for the first iteration. Let's not worry about the post condition just yet. Normally, we should really check it only at the end. For now, it's not applicable. to check it just yet. All right, let's now go on to see the iteration. Okay, let's do a few, and then we can fill it out accordingly. So let's say for the very first iteration, okay, we start with the I value being 1. Okay. Oh, think about it, it's more like a I will be changed to 2. Okay, let me just say it's going to be changed to 2. Okay, because we got I is assigned to I plus 1, right? 2. Okay. And then after that change, we're going to evaluate this looping variant here. So now 2 is still within this range. So looping variant is maintained at the end. Maintained. All right. So after this, we're going to check to see whether 2 is less than or equal to 5. It is. Okay. That means we're going to go for third iteration, and so on. Okay. Let's follow the pattern, right? I don't need to trace any more in detail. Okay. So now let's now try to see if I go for second iteration, I'm going to change the value to 3, still within the range between 1 and 6. So I'm good. It's still maintained. And then 3 is still less than or equal to 5. Good. Go for another iteration. Okay. Okay, number 3, in which case it's going to be incremented from 3 to 4, and it's still within the range. Okay. Here, and then we should still go on for another iteration. Okay. So now one more. Getting there. 4, and then incremented from 4 to 5, and 5 is still satisfying the looping variance. Right here, and then 5 less than or equal to 5. Good. Go for one more iteration. That's why we got 5. Right? Let's continue, and I'll show you the edge case at the end, which is important to get right. So we get 5 here. It's going to be incremented from 5 to 6. All right. So now, at the end of the 5th iteration, I'm going to highlight this one specifically. At the end of the 5th iteration, have we maintained the looping variance? Have we? You check to see 6. Does it satisfy this constraint? It does, right? Good. Okay. That's important, right? I want to be sure. So that one there, good. All right. And now, when I evaluate 6 against this condition, true or false? False. Exit from the loop. So now I'm actually going to, that means exit from the loop. All right. Now, you can think about, we are basically now checking to see whether this can be the case. Now we actually got another case, I less than or equal to b. And also we got the looping variant as well. Also satisfy, maintain. Now we want to see how exactly the post condition will be like. Right? Let's see. Now this part here is a post condition. If you only check to see the value, I'm going to show you one predicate as well. Check to see whether I is exactly equal to 6. It is. Okay? At the end, right here. So there is a general formula that we need to know. Okay? Which goes like this. Okay? So in general, when you exit from the loop, not B, when the state condition is not true. And we know that at the end of the very last iteration, the looping variance should still be maintained. That one logically should really entail the post condition. This is a formula we want to really keep in mind. And then we're going to see that for different example. Okay, at least the one that's going to be on Friday. Okay, I'm going to write it down. The annotation. So this one means we want to exit. And this one means the looping variance is maintained in the last iteration. Maintained in the last iteration. logically, we should be able to prove that the post condition is established. The post condition should be established. In our case, let's see if that's the case. Very simple logic to show. Okay, let's now see in our example. Okay, I'll continue from here. Okay, put a star. Okay, in our case, the b here, I less than or equal to 5. Okay, not the case, I less than or equal to 5. And also looping variance is right here. And 1 less than or equal to I less than or equal to 6. All right? So now, can we show that this implies the post condition right here, which is I equals 6. It is, right? Obviously, because you can see, well, just simplify this by I larger than 5. Given that should be larger than 5 and also between 1 and 6, the only possible value will be it is 6. Okay, simple one, just to get an idea. All right, so this one can be easily shown as provable. All right, so this can be proved. All right, good. And normally you don't really check to see whether post condition will be established in all the previous, except for at the end of the last iteration. Okay, let me recap very quickly, and then I will give you 2 exercises, and then we can take a short break, a little bit earlier than usual. Okay, so given any algorithm, iterative algorithm, let's say while loop, and with some variable assignments, we'll see something a little bit more complicated on Friday. You ought to specify precondition, postcondition, before and after the algorithm, and then you have to insert the looping variant in 2 places. One will be right before we check to see whether we should stay in the loop for the very first time, to see if the looping variant is established. And then at the end of each iteration, we're going to see if the looping variant is maintained. Okay? And you can definitely use a table to trace it. Okay? In general, this will be the formula we want to honor, really, right here. Right here. Okay? NABI means we are ready to exit from the loop. Li means we still have the looping variant maintained from the very last iteration. That should really logically entail the post condition. Okay? All right, very good. And 2 exercises for you. Okay. Now consider changing this looping variant here. Let's say you have looping variant, let's say prime, just a different one, okay, modified version. Let's say that one there is simply 1 less than or equal to I less than or equal to 5. Okay. Number 2, looping variance prime prime. Okay, another version. That one there, let's say 1 strictly less than I, and then less than or equal to 6. Very subtle changes. However, you got to be very careful about using this looping variant here to see whether it's going to be established and also maintained. All right. Questions? Okay. All right. Why don't we take a short break, and then we'll continue after the break. Okay, so I think before the break, we spoke about this example about looping variant. There's another way if you want to visualize what's going on. It's just another visual way to actually see it, okay, to see if that might help you. Okay, so basically think about every time we have some iterative algorithm, so you can think about at this point over here, this is like we call it a pre-state, but don't worry about the term. We're just saying starting point. You can think about this as a starting point. Starting point of your algorithm, iterative algorithm. In that way, you have to make sure Q, the precondition, must be satisfied, right? Make sure you do that. And then you have some initialization. this initialization here in the diagram is really corresponding to S init. You got to do something to kind of prepare for the loop. After the initialization, the very first time we check for looping variance is exactly right here. Okay, I'll highlight it. You can see this point here is really the very first point, the starting point for the first iteration. The looping variance established right here. Okay, and then of course at this point here, assuming that B, the while, the B, the state condition is also true. And then you got to keep doing the iteration for as many times as necessary, right? Right here, okay? So now you can think about now the checkpoint, right? So now, since we already do this one here already, we got to make sure after, at the end of the first iteration, check to see if the looping variant is maintained. At the end of the second one, check to see if that's maintained, and etc. Right? I'll just put one of them. So you can think about right here. At the end of the first iteration, the looping variance is maintained. You can go for as many iterations as you like. When we actually get to the final point, that's actually after the very final iteration, okay? So which will be this point here, okay? Let's put it here. So this will be the final point, right here. This final point here is actually after, you can think about this thing here, is the last iteration. Okay, so here we're saying after or at the end, that's better. At the end of the last iteration. Okay, we got several things that should be true. Number one, the condition for the while loop should be false. Otherwise, we'll go for another iteration. The current one wouldn't be the last one. Okay? That means we want to exit from the loop. Number two, the looping variance should be still maintained. And then, logically, it should also entail that the post condition is also true. So these are the three things: not B, looping variance, and the post condition. But post condition should be entailed logically by the fact that we can exit, and also the looping variant has been maintained. So that's why you can think about here, this one here is more like an intersection about this part here is the looping variance being maintained. This part here is about the condition for us to exit. And this part here is about the post condition being satisfied. It's like an intersection for all the sets. Okay. Okay, so this exit condition here, right, just another way to say not B. Okay, B is a state condition. Not B means exit. All right, just another way to understand about the terms right here. All right. Questions? Yes.
I'm a bit confused because it shows that B, or is that whole blue oval like the body of the loop?
Yes. Oh, okay, good question here. To be more precise, each individual line, think about here. Okay, I know exactly what you're confused about. The body here is the same as the body here, like a repetition, right? Think about here, let me show you exactly. So here, when we say while, and then we say the body statement. So this body here may be run for as many times as you like for each iteration. Right? So now we're saying this. This is the start for the first iteration. After executing the body statement for the first time, we get to the end of the first iteration. At the same time, the beginning of the second iteration. Execute it for the second time. So now get to the third iteration and execute it, and so on. The very last line here will be the very last iteration. At the end of it, we want to make sure the looping variant is still maintained. It's always maintained after the iteration. But this is the last iteration because at the same time, the Boolean condition is also false. Right? Given that the Boolean condition is false, that means we are ready to exit. given that we are ready to exit and the looping variant is also maintained, logically, that should entail the post condition should be established. That's usually something we want to show logically. I'll do more example about this implication proof. Yeah.
I have another question.
Go ahead.
Where on the diagram with the first assertion of the
Establishment, right? Yeah, good question.
is that also like where the D is? So it's not like
Yeah, exactly. So you can think about we kind of start. This will be the starting point for your algorithm, right? So as soon as you start, you want to make sure the precondition is satisfied. Let's say you want to make sure all the weights in the graph are non-negative. Check that first, and then you're gonna do some preparation for your loop, and then you gradually move it into right before you check to see whether it should really stay in the loop for the very first iteration. You gotta make sure at that point there, the looping variant is also established. That's the first point. So you can think about checking this point for the first time for establishment, and then at the end, each time, you're gonna check for maintenance. Okay, yeah. Yeah, I think this diagram here is really nice, really conceptually just clarify about how the precondition, postcondition, looping variant, they can all work together, okay? Okay, good. Now let's revisit our Dijkstra algorithm a little bit, okay? So I wouldn't really try to do this implication proof just yet for today. Okay, I'll do that maybe a little bit later. But today, let's now look at how the looping variant can be fit into this context, given that we got some understanding already, okay? So this is the slice right here. Okay. So I'm talking about slide number 65. Okay, right here. Okay. The looping variance basically goes like this. That's something we already kind of informally learned from the tracing. That's why I kind of mentioned that without saying there's a looping variance. Let's now revisit the tracing from Monday. Okay, that's something you can definitely revisit as well after class today. Whenever I said the capital D is equal to the true distance, like a minimum shortest path, whenever we have tried to remove a particular vertex from the queue, from the priority queue. So basically this, you can think about this part over here tells us about the looping variant because that's right at the end of the iteration. All right, so now imagine, let's think about informally. The looping variant is something we want to be true at the end of the iteration, okay? So now at the end of the very first iteration, we know that W has already been removed from the priority queue. It's gone. So now we can say something final about that removed vertex. We can say that for W that has been removed already, its capital D value is now already equal to the lower D value, which specify the true minimum distance between the vertex W and also the source vertex, which happen to be W as well. Question?
I was thinking about this earlier, for Dijkstra specifically. Do our assertions have to be like, I don't know what the term is, but like evaluatable? Like we don't know.
It's a very good question. Yeah. So I would say
we don't know the true final distance until we're done.
it's a very deep insight. Actually, I like it. Right. So what Josh is asking is, if we somehow based on the example we learned earlier, you want something to be runnable at a runtime, right? It's a very valid question here. You're basically saying, here, how do we know what this is in order to evaluate it? If we know what it is, why should we bother to even calculate it, right? That's kind of where you're going. I would say for Dijkstra here, we can maybe restrict ourselves more on the paper exercise to see conceptually why it's working for correctness proof. That's something we'll do, for the assignment number 2. But I think there will be other example where it's actually much easier to specify some evaluatable condition, which we'll see on Friday. Okay, good, very nice. Yeah, in some way you're right. This one here is some value that if we can know that beforehand, why should we even bother to calculate it, right? So here it's more like an oracle value that we can assume we have. Yeah. All right. Anyway, so when you revisit the looping variant for after today, you just want to remember whenever we say remove a particular vertex from the priority queue, after that, that particular vertex should have its capital D value exactly equal to the true value. We don't really have to update the D value for that anymore. We don't have to. It's a very important looping variance to know. Okay, check at the end of every iteration. But now, let's now do something that's going to help your assignment number 2 a little bit. Okay. Okay, let me just mention that right here. Okay, I'll give you a little bit more hints. So let's read it together, right? So that's just about the facts about when we should check about the loop invariance. So here we say that for every vertex U that has already been removed from the priority queue, right? Could be W, can be Z, can be Y, can be X, right? And it's considered visited once it's removed. We say that the capital D value is more like the minimum length so far. It should be exactly equal to the true shortest distance. And this one here will be D, and then from the source S to U. Okay, so we are saying that these two are the same. Exactly how we have traced the Dijkstra algorithm back on Monday. All right. Let's now try to do a simplified version of the tracing very quickly so we can see exactly how that's going to work. Okay. So let's now see our context, right? So what we have is we have some input graph, and then we got a set of vertices, we got a set of edges. And let's say we want to apply the Dijkstra algorithm. Dijkstra from some source vertex, let's say S, which is one of the vertices. Okay, so that's the source we want to start with. Okay, and then we can now do a trace table quickly. Let's say let's use our example. Okay. Okay, again, let's now try to do right here. Let me put 1, 2, 3, 4 columns in total. Okay, right here. Number 1, let's say the iteration. And also, what do we remove in that particular iteration? And at the end of the iteration, is the loop invariant true? And also, let's now consider a set S. So this capital S set is actually mentioned as a hint in your assignment number 2 question. Maybe it was question 1 or question 3, I forgot. One of them, about the proving correctness question. Okay? So the S over here is about the set of vertices removed so far. Eventually, capital S should be exactly equal to V once we have removed everything from the priority queue. Okay? So let's now take a look. Okay, let me also remind you very quickly. Oh, sorry. Right here. Okay. So let me remind you from last time for the tracing right here. The order that we remove the vertices will be W followed by Z followed by Y followed by X, right? Just remember, okay? So I'm not going to repeat the details. I just use the table here to simplify the observation, okay? So there will be 4 iterations in total, okay? So we're going to get 4 rows right here. 1, 2, 1, 2, 3, 4, okay? At the end of the first iteration, second, third, and fourth. Okay, so I really meant to say at the end. At the end of the iteration. Okay. You might be thinking, what about establishing the loop invariance? You might be thinking, right? Let me handle that as more like a special case that will require some special property for implication. I'll get there a little bit later. Okay, let's focus on just the maintenance itself. Okay, for that one there, so we're going to remove in the following order. We're going to remove W, remove Z, remove Y, and remove X. Okay, and then after the very first iteration, S will be exactly just W. That's what we have removed so far, right? And then the second one is going to be W already removed also Z. The third iteration is going to be W, Z, and then Y. You can think about after each iteration, the priority queue is shrinking, and also the S is being increased. It's basically growing. And then after the very last iteration, we got W, Z, Y, and then X. Okay? And then let's see what we have right here. Okay? Let me try to write one or two individually just for you to see how it's supposed to work. And then we try to generalize it using universal quantification, right? We'll go step by step. So let's say at the end of the first iteration, okay? We know that right here, the capital D of W is equal to the lower d of from W to W itself. All right? That one can definitely revisit to the tracing table. Okay? That's it. Okay? Let me be a little bit lazy here. Let's say this is the loop invariant I check back in. Let's say loop invariant I check at the end of the first iteration. I put a subscript 1 there. Okay? So now, at the end of the second iteration, what do we have? We basically have whatever that's before, it doesn't change. It's still satisfied. And since we just remove Z, it's going to be D of Z equals cap lower d from W to Z. Follow? That's a new condition we're adding, right? We're just accumulating. And let's call this condition over here the loop invariance at the end of the second iteration. Okay, you can see the pattern here. Let's do one more. Okay, let's just continue. This will be Li2, and since we just remove Y, it's going to be D of Y equals little d from W to Y. Let's call that over there Li at the end of third iteration. Okay, do one more, and then we'll see how we can generalize it. And then after that, we can say Li3, and then D of X, right? Equals little d, W to X. Let's call that one there Li4. Okay, follow so far, right? You can see the pattern here. Okay. If you somehow understand about the individual equality that we are establishing, that's a very good sign. But now we want to make it general. Okay? How do we specify the loop invariant in general? So there are two ways to do this. Okay? One way is you can simply just argue the fact that if the vertex does not exist in the priority queue Q, that means it should really satisfy that equation. That's one way to do it. I'll show you. Another way to do it is to argue about as long as the vertex is a member of this particular set, we know that it should really satisfy the pattern for equation like that, right? They're really similar, okay? Let's show you both, okay? Let me start with the version that's on the slides, okay? So loop invariance version 1, okay? I can say for every vertex U, given that the vertex is not in the priority queue, it's not in the priority queue, that means conceptually it's already final and visited. Final and visited. Okay? Of course, you can also say U is also a member of the capital V, right? It's a valid vertex. You can say that as well. And U is actually a member of the capital V. And I'm talking about a V here, okay? It should be it's a valid vertex. So that would mean exactly this. The capital DB of U is equal to lower d of, starting from the start vertex, S to U. Okay, that's the first version. in our particular example, you can think about the S over here is really the starting point W. Okay, I'm just instantiating it. Okay. Are we okay with the first version here? Right, we're just saying that as long as we consider all the vertices that's not in the priority queue. And for those vertices, they should have this particular equation holding. Okay, right here. That's one way to do it. Another way to do it is by using this set over here. You can think about this set in some ways more like a final set about all the vertices whose result have been finalized. So that one there, let's say put it here. Loop invariance version 2. Okay, running out of space, I'll say star. Okay, you can say for every U, first of all, U should be a valid vertex V. And U is a member of capital S, right? I'm talking about an S right here. So that would mean that particular equation, right? So D of U equals little d from the source vertex S to U. And for our particular example, it's simply W, right? That's the second version. And of course, you should know both. The difference is we are just using the fact that it's not in this particular set, or the fact that the vertex has been removed. They are really saying the same thing, because we only add the vertex into S when the vertex is removed from the priority queue, right? They really mean the same thing. Yeah. So this loop invariant here is gonna should be maintained between the iterations. Doesn't matter how many iterations you might have. Questions? Okay, okay. Hopefully that's clear. All right. And then let's now do, okay, I think we can do one more, at least one more thing. Okay. Let's now talk about another very fundamental assumption that we're making about Dijkstra algorithm. We say that the weights for each edge must be non-negative. It cannot be negative because we said that somehow it's not going to work. Let's see one example why it wouldn't work. Okay, simple example. Okay, let's take this one. Very simple. First of all, how many iterations do we need for applying Dijkstra? How many? How can we tell? Huh? 3? Yeah, we got 3 nodes, 3 iterations. Yeah, because initially we add A, B, and C into the priority queue. We got to take 1 out each iteration. So 3 iterations in total. All right. Let's now do what we did, like on Monday. So let's now, first of all, let's now figure out what's the lower d, the true value for distance. So let's say we want to start with A. Okay. Let's say. So from A to A itself, and also lower d from A to B, and also here from A to C. Oh, notice that, don't lose the big picture. The reason that we want to do another example is because you can see now we got negative weights. So this example is going to show to us Dijkstra algorithm might run into trouble, okay? Because we break that assumption. What should this be? A to A? 0? Yeah, always 0, right? Now, what about from A to B? 2, 1. Be careful. Definitely can go here, or it can go here. In which case, the negative value is going to offset the 4, which will give you 1. Watch out. Okay, this is the main thing. Okay, we're talking about a true value. However, somehow, Dijkstra algorithm, in this case, I'll give you a little bit preview. Dijkstra algorithm, when it removes vertex B from the priority queue, meaning that the B value should be final. In that case, it's not going to reach to 1. That's a problem. All right? Okay? But we can see exactly. Okay? And then A to C. 4? Yeah, you actually have only one way to get there, right? That one, no brainer. Okay? 4. Very good. Let's keep this in mind. And then let's now do a tracing table quickly. Okay. So let me just remind myself, what did I put? Give me one moment. Let's do this one, and then we should be good for today. Iteration minimum changes. Okay. Right here. Okay, let's do that quickly, and then back carefully. So what we have is right here. So we got iterations, and also we got the minimum d value that we're going to get, and also we got the changes. Of course, we could have drawn another table for initialization, but let's be a little bit quicker. Okay, let's not initialize first of all. Okay, so let's write it down. So the d of a, the source should be 0, whereas the d value, capital D value for the rest, should just be infinity, right? Make sure you're confident with this. D of c will be infinity. Let's not worry about ancestor for this, because that's not the main point. Okay? Because if you set the minimum value to be wrong, d value to be wrong, the ancestor will be wrong as well. So let's focus on the capital D value just for this one here. Okay? And let's draw the cube. Right here. That's our priority cube. And then we're going to initially add all the vertices in. Doesn't matter the order. But let me just put A, B, C, right? So now iteration number 1. We are actually going to pick the minimum. So which one has a minimum? Stop vertex, right? Guaranteed, right? So we're going to take A, because the capital D value of A is equal to 0. All right? So that means we're going to go from here. Okay, be careful. Okay, right there. And then we know that we can reach out to 2 vertices because both neighbors, by using the incident edges, you can see B and C, they are still in the priority cube. So we should consider them. We don't skip. All right? So now we are going to do here, the changes will be, first of all, B is in the queue. And also C is also in the queue. Okay. So now what do we check? 0 plus 2 is less than infinity. 0 plus 4 is also less than infinity, right? So let me now write the equation down. We know that pretty well. Okay? So what we do is we're going to say capital D of B is changed to 2. Capital D of C is changed to 4. Okay? So this one should be 2, and this one here should be 4. Okay? So far, so good. After this, we're going to remove A from the Q. And now we know that capital S, right? Let's now put a final set. That one there should really contain A. A is already final, so we don't consider A anymore. Right here. All right, that's the first iteration. And let's now go on to the second iteration. Right here. And for the second iteration, we're going to pick, oh, actually A is removed, right? So let me just don't forget. So A is removed, the first one. All right. And out of B or C, which one's minimum? B, right? Let's pick B. All right. Thank you. So why don't we pick B? For the second iteration, we're going to pick B because the D of B is equal to 2. All right. So pick that. So for that one there, we're going to pick right here. Because this graph over here is directed, so is there any outgoing edges? Not really. So we're good. All right. We don't need to consider anything. Okay. No change. No change. And then we are actually going to remove B from the Q. That means the capital S over here contains A and B. Now, can you already see a violation of the loop invariance, right? Because if now you look at right here, okay, this is important. Remove and then get here, right? At this point, you can see, let's isolate this value here. And also right here. Do they match? They don't. But we said that this is supposed to be final. It's not final. It's not reaching there. Okay, write it down first, and then we'll go on for the third iteration, and then we'll see. Okay. I also want to point out some external reference for you. So now, right here, okay. If you compare these two values, I'll put a star. At the end of the second iterations, the removed vertex B final value, which is 2. Which is not equal to the true D of A to B, which is equal to 1. Okay? So it is a violation of the loop invariance. Let me continue with the third iteration. There's another point I want to make, right? Let's speak for completeness. But this is very important for you to realize we got loop invariant violation right here, okay? Violation, right, of loop invariance. Let's now go on to do the third iteration, the last one. So after this, we actually got B removed, number 2. Let's now go to third iteration, okay? This is critical, all right? So for third iteration, we have the minimum should be obviously C, all right? Let's write it down. So let me put right here C. Okay, we're going to choose that. So the third iteration, we're going to get C because the capital B value for C is equal to 4. So now, there's only one vertex going out. It seems like when we do this one here, 4 plus minus 3 is less than 2. Then we should really update this one here to be 1. Should we do that? Let me say that again. Guys, this is the most critical point, right? Let me say that again. In the third iteration, we pick C. The only incident edge we have has the weight minus 3. And the D value for C is 4. 4 plus minus 3 is strictly less than 2. Should we update this to 1? No. Why should we not update it? Yeah, we already removed, number one, we already removed B, right? And remember, there's a very important line in the algorithm, right? That's the most important thing to notice, okay? If you go back to the algorithm itself, we'll talk about its runtime on Monday, okay? Next Monday. This condition here, it's got to be in the queue, but it's not. So we don't even consider that, all right? So now here, important to say here. So B is not in the queue anymore. No change. And then we are done. So as far as the Dijkstra algorithm is concerned, this will be the final values for A, B, and C. So you can see for A and C, they are correct, but for the B, it's wrong. Of course, it's a very, very small example. If you make the graph a little bit larger, you might get more than one node whose true value doesn't really match the final D value. Okay? I will speak more about this, about why the Dijkstra algorithm wouldn't actually go ahead and go into the node that has already been removed and do it. It's because if you try to do this kind of an edge as well, it's going to increase the running time very badly. Okay? And then I'll just show you one more thing. Okay? But there is certain algorithm that's going to extend the Dijkstra to actually check this kind of edge to really update the value as well, to make sure it matches the real D. I mentioned the name, but we wouldn't be able to cover that in this course. Okay? For those of you who might be interested, I'll talk about runtime more precisely on Monday. So it is called, okay, so let me see, did I put it here? Okay. Okay, maybe I didn't put the name here, but anyway, let me stop here, and then on Monday we're gonna just go back to the running time about Dijkstra, and then we'll mention the name for the algorithm as well. All right. Anyway, so please make progress on your assignments, and then on Friday we're gonna talk about more example about loop invariance. Thank you.